Hello everyone, myself Assistant Professor Vatsal Patel from Civil Engineering Department working at Mahatma Gandhi Institute of Technical Education and Research Center NAVSARI. Today we are going to discuss about theory of errors, and our today's topic is theory of least squares and distribution of errors. So be ready with your pen and paper. So let's start with the theory of least squares first. So the principle of distributing errors by the method of least squares is of the great help to find the most probable value of a quantity which has been measured for several times. It is found from the probability equation that the most probable values of a series of errors arising from observations of equal weights are those for which the sum of the squares is a minimum. The fundamental law of least square is derived from this. So, the fundamental principle of the method of least squares may be stated as follows. In observation of equal precision, the most probable value of the observed quantities are those that render the sum of the square of the residual error a minimum. So, if the measurements are of equal weight, the most probable value is that which makes the sum of the square of the residue, or it is denoted by small v, which is a minimum. Thus, sigma v square is equal to a minimum, or summation v square we can say a minimum. And if the measurements are of unequal weight, the most probable value is that which makes the sum of the products of the weight, say small w, and the squares of the residuals a minimum. Thus, sigma w into v whole square is equal to minimum, or we can say summation w v whole square is equal to a minimum. So let us understand it with some procedure. So when a quantity is being deducted from a series of observations, the residual error will be the difference between the adapted value and the several observed value. Okay. So if we talk about this, let x1, x2, x3, x4 be the observed value and z is equal to the most probable value. So then z minus x1 is equal to e1 and z minus x2 is e2, z minus x3 is equal to e3 plus up to plus z minus xn is equal to en, where e's are the respective residual errors of the observed values. So this will be our equation number 1, all this, okay, from z minus x1 is equal to e1 to z minus xn up to en, okay. So it is our equation number 1. Next, if capital M is the arithmetic mean, then M is equal to x1 plus x2 plus x3 plus up to plus xn divided by n, or we can say sigma x divided by n. So which is our equation number 2, where small n is equal to number of observed values. So from equation 1, nz minus sigma x is equal to sigma e, or we can say z is equal to x by n plus sigma or we can say z is equal to sigma x divided by n plus sigma e divided by n. But here from equation number 2 we know that sigma x divided by n is equal to m. So putting that value, z is equal to m plus sigma e divided by n. So if the number of observations is large, n is very large, and e is kept small by making precise measurement, and the second term sigma e divided by n becomes nearly equal to 0. So z is equal to m plus sigma e divided by n will be our equation number 3. Thus z is equal to m. Thus when the number of observations is large, the arithmetic is the true value or most probable value, or we can say z is equal to m. So now we calculated the residual errors from the mean value. If v1, v2, v3 etc. are the residual errors, then m minus x1 is equal to v2. m minus x1 is equal to v1, m minus x2 is equal to v2, m minus x3 is equal to v3, plus up to plus m minus xn is equal to vn. So this will be our equation number 4, from m minus x1 is equal to v1 to m minus xn is equal to vn. So adding the above equation, nm minus sigma x is equal to sigma v, or we can say m is equal to sigma x divided by n plus sigma v divided by n. So as we know, m is equal to ax by n, and under the preceding conditions and by preceding equation, and hence sigma v divided by n is also equal to 0. So hence the sum of the residuals equals to 0, and the sum of the plus residual equals to the sum of minus residuals. So this is our theory of least squares. Next is rules for giving weights and distribution of errors to the field observation. So let's see rules for giving weights to the field observation first. So the weights of an angle varies directly to the number of observations made on the angle. The weight of the level lines vary inversely as the length of their roots. The weights of any angle measured a large number of times is inversely proportional to the square of the probable error. And the correction to be applied to various observed quantities are in inverse proportion to their weights. Next is distribution of errors to the field observations. So whenever observations are made in the field, there is always some error, or we can say accidental error. It is always necessary to check the observations made in the field for the closing error, if any. The sign of correction is opposite to that of the closing error. The closing error should be distributed to the observed quantities. For example, the sum of the angles observed at a central triangulation station should be 360 degree. If the sum is not equal to 360 degree, the error should be distributed to the observed angle after giving proper weightage to the observations. So the following rules should be applied for distribution of errors. The correction to be applied to an observation is inversely proportional to the weight of the observation, or in other words, the greater the weight, the smaller the correction. Next, the correction to be applied to an observation is directly proportional to the length of the probable error. In case of line of levels, the correction to be applied is proportional to the length of the root. If all the observations are of the same weight, the error is distributed to observed quantities equally, and therefore the corrections are equal. So let's see some examples on distribution of errors. So here is the data, you can write down it. Okay. So the following are the three angles, say A, B and C, observed at a station O closing the horizon. Along with their probable errors of measurement, determine their corrected values. So values are A is equal to 82 degree, 15 minute, 20 second, plus or minus 2 second. B is equal to 128 degree, 26 minute, 10 second, plus or minus 4 second. And C is equal to 149 degree, 18 minute, 15 second, plus or minus 3 second. Sorry. So let's see the solution. So sum of three angles will be 359 degree, 59 minute, 45 seconds. So what we have done, we have summation of these three values. So discrepancy will be 360 minus sum of three angles, which will be 15 seconds. So hence each angle is to be increased, and the error of 15 seconds is to be distributed in proportionate to the square of the probable error. So let's see its solution. So let C1, C2, C3 be the correction to be applied to angles A, B and C. So C1 jam C2 jam C3 is equal to 2 square plus 4 square plus 3 square, which is 4 jam 16 jam 9, which is our equation number 1. Sorry. And C1 plus C2 plus C3 is equal to 15 seconds, which is our equation number 2. So from equation 1, C2 is equal to 16 divided by 4 C1. Therefore, C2 is equal to 4 C1 and C3 is equal to 9 by 4 C1. So substituting these values of C2 and C3 in equation 2, the equation will be C1 plus 4 C1 plus 9 divided by 4. 9 by 4 C1 is equal to 15 seconds. So if we simplify it, C1 is equal, C1 into bracket 1 plus 4 plus 9 by 4 C1 is equal to 15 seconds. So our final equation will be C1 into bracket 5 plus 9 by 4 C1 is equal to 15 seconds. So from this C1 is equal to 15 into 4 by 29, which comes our value is 2.07 seconds. C2 will be 4 into C1, so 4 into 2.07 seconds. So answer will be 8.28 seconds. C3 is equal to 9 by 4 C1, so 9 by 4 into 2.07 seconds. So answer will be 4.65 seconds. So if we apply the check, C1 plus C2 plus C3 is equal to 2.07 plus 8.28 plus 4.65, which is equal to 15 seconds. So it is accurate. So hence corrected angles are A, B and C will be 82 degree plus 82 degree 15 minute 20 second plus 2.07 seconds. So our final angle A will be 82 degree 15 minute 22.07 second. If we talk about B, 128 degree 26 minute 10 seconds plus 8.28 seconds. So our final angle will be 128 degree 26 minute 18.28 seconds. And for angle C, 149 degree 18 minute 15 second plus 4.65 seconds. So our final angle C will be 149 degree 18 minute 19.65 seconds. So if we do summation of these all three angles, the total will be 360 degrees 0 minute 0 seconds. So it is okay. Next is another sum here, so you can write down the data from here. So example on distribution of error, the data is adjust the following angles closing the horizon. Angle and weight are given. Angle A is equal to 112 degree 20 minute 47 second and weight is 2. Angle B is equal to 90 degree 30 minute 15 second, weight is 3. C is equal to 58 degree 12 minute 5 second and weight is 1. And D is equal to 98 degree 57 minute 0 seconds and weight is 4. So let's see solution. So summation of all these 4 angles. Which angles? All these 4 will be 360 degree 0 minute and 08 second. So discrepancy will be 360 minus the sum of 4 angles. So 360 degree 0 minute 0 second minus 360 degree 0 minute 08 seconds. So our answer will be minus 8 seconds. So hence each angle is to be decreased and the error of 8 seconds is to be distributed into the angles in an inverse proportionate to their weights. So let's see its solution. So let C1, C2, C3 and C4 can be the correction to be applied to angles A, B, C and D. So C1 jam C2 jam C3 jam C4 is equal to 1 by 2 jam 1 by 3 jam 1 by 1 jam 1 by 4. So our equation will be C1 jam C2 plus C1 jam C2 jam C3 jam C1 will be 2 jam 4 by 3 jam 4 jam 1, which is our equation 1. So here you will all have answer where this come from. So only we have simplified above equation by 4 and hence it comes as equation number 1. And C1 plus C2 plus C3 plus C4 is equal to 4 seconds, which is our equation number 2. So from equation 1 we have C1 divided by C2 is equal to 2 by 1 into 3 by 4, which is 6 by 4. Therefore C2 is equal to 4 by 6 C1 and C2 is equal to 2 by 3 C1. C1 by C3 is equal to 2 by 4. Therefore C3 is equal to 4 by 2 C1. So C3 will be equal to 2 C1. C1 by C4 is equal to 2 by 1. Therefore C4 is equal to 1 by 2 C1. So substituting these values of C2, C3, C4 in equation 2, we get C1 plus 2 by 3 C1 plus 2 C1 plus 1 by 2 C1 is equal to 4 seconds. Therefore C1 we have to take common. So 1 plus 2 by 3 plus 2 plus 1 by 2 is equal to 4 seconds. Therefore C1 is equal to 4 into 6 by 25, which is 24 by 25. So our answer will be 0.96 seconds. Therefore C2 is equal to 2 by 3 C1. So putting the value of C1, so 2 by 3 into 0.96 is equal to 0.64 seconds. Same as C3 is equal to 2 C1. So 2 into 0.96, so our answer will be 1.92 seconds. And lastly C4 is equal to 1 half C1. So it is 1 half into 0.96, which is 0.48 seconds. So hence corrected angles are A is equal to 112 degree 20 minute 47 second minus 0.96 seconds. So our final angle A will be 112 degree 20 minute 45.04 second. If we talk about angle B, 90 degree 30 minute 15 second minus 0.64 second. So our final angle will be 90 degree 30 minute 13.36 second. If we talk about C, 58 degree 12 minute 5 second minus 1.92 seconds. So our final angle will be 58 degree 12 minute 2.08 second. And lastly, if we talk about D, 98 degree 57 minute 0 second minus 0.48 second. So our final angle will be 98 degree 56 minute 59.92 second. So if we do the summation of all these value, the total will be 360 degree 0 minute 0 second, which is okay. Next we are going to discuss about determination of the most probable values of quantity. So as defined earlier, the most probable value of a quantity is the value which has more chance of being true than any other value, or we can say close to the true value. So the most probable value is therefore a value which is very close to the true value. This value is derived from several measurements of the quantity. The most probable value of a quantity can be determined from the principle of least squares. The theoretical basis of this principle is the assumption that the accidental errors will wholly disappear from the mean of an identifiedly large number of independent observations taken under precisely similar conditions. Therefore, if systematic errors are eliminated from the observation, the arithmetic mean will be the most probable value of the quantity being observed. So, in practice, the following cases may arise of which the most probable value may be required to determine. So, the determination of most probable value is given by first the direct observation. Next, it is further divided into two parts: direct observations of equal weights and and direct observations of unequal weights. Next is indirect observations. It is also divided into two categories: indirect observation involving unknown of equal weights, and second one indirect observation involving unknown of unequal weights. And lastly, observation equations accompanied by condition equation. It is divided into three parts: the normal equation, the method of differences, and the method of correlates. So let us see it in the detail. So let's talk about case 1, which is direct observation of equal weight. So the most probable value of the directly observed quantity of observation of equal weight is the arithmetic mean of the observation. Thus, if x1, x2, x3 up to xn be observed value of a quantity of equal weights and x be the most probable value of that quantity, and n is equal to number of observation, our equation will be x is equal to m is equal to x1 plus x2 plus x3 plus up to plus xn divided by n. So let's see example based on case 1. So data is given here. Following direct measurements of a baseline were taken, like all the notation are given here, like 2523.32 meter. Same as all data are here. Okay, you can write it down in your notebook or paper. So we have to calculate the most probable value of the length of the baseline. So as we know the solution, most probable value is equal to arithmetic mean capital M. So our equation is x is equal to m is equal to x1 plus x2 plus x3 plus up to plus xn divided by n. So where m is equal to arithmetic mean of the observed values, and x1, x2 up to xn are the observed value of the quantity, and small n is equal to number of observation. So our equation will be putting the value m is equal to 2523.32 plus 2523.25 plus 2523.17 plus 2523.38 plus 2523.47 plus 2523.68 divided by 6. So our answer will be 2523.378 meter. So the most probable value of a baseline length x is equal to 2523.378 meter. So which is our required value. Next, let's see the case 2, which is direct observation of unequal weight. So the most probable value of the directly observed quantity of observations of unequal weights in the weighted arithmetic mean of the observations. Thus, if x1, x2, x3 up to xn be the observed value of a quantity, and w1, w2, w3 up to wn be their weights, and let x be the most probable value of this quantity, and small n is equal to number of observation. So our equation will be x is equal to w1 x1 plus w2 x2 plus w3 x3 plus up to plus wn xn divided by w1 plus w2 plus w3 plus up to plus wn. So let's see example based on case 2. So here the data is given. Find the most probable value of the angle from the following observation. Angle A is equal to 76 degree 35 minutes 0 second, weight 1, and angle B is equal to 76 degree 33 minutes 40 second, weight 2. So let's see solution. So most probable value is equal to the weighted arithmetic mean of the observed quantities. So our equation will be x is equal to w1 x1 plus w2 x2 divided by w1 plus w2. So 1 into 76 degree 35 minutes 0 second plus 2 into 76 degree 33 minutes 40 seconds divided by 1 plus 2. So our answer will be 76 degree 33 minutes 6.67 seconds. Next is case 3. Indirectly observed quantities involving unknowns of equal weights. So in this case, the most probable values of the unknowns are generally found by the method of normal equations. To form normal equation, multiply the equation by their coefficients of unknowns and add the results. So let's see the example based on case 3. So here is the data. Find the most probable value of the angle A from the following observation equations. Angle A is equal to 30 degree, 28 minute, 40 second, weight of 2. And angle 3A is equal to 91 degree, 25 minute, 55 second, weight of 3. So let's see its solution. So most probable value is equal to the normal equation of A. So multiply the first equation by 2, or we can say 1 into 2, and second equation by 9, or we can say 3 by 3. So 2 into A is equal to 2 into 30 degree, 28 minute, 40 second. So further it is simplified. Twice A is equal to 60 degree, 57 minute, 20 second, which is our equation 1. Next is 9 into 3a. So 9 into 91 degree, 25 minute, 55 second. Further it simplified. 27a is equal to 822 degree, 53 minute, 15 second, which is our equation 2. So sum 1 plus 2. Okay, so 2a plus 27a will be 29a. So summation will be there. So our final answer will be 883 degree, 50 minute, 35 second. So angle A will be 883 degree, 50 minute, 35 second divided by 29. So our answer will be 30 degree, 28 minute, 38.45 seconds. So the most probable value of angle A is equal to 30 degree, 28 minute, 38.45 seconds. Now let's see the case 4. Indirectly observe quantities involving unknowns of unequal weights. So in this case, the most probable values of the unknowns are generally found by the method of normal equations. To form normal equations, multiply each observation equation by the product of the algebraic coefficient of unknown quantity in the equation and the weight of that observation, and add the equation thus formed. Next is case 5. Observation equations accompanied by condition equation and condition quantities. So in the case of conditions quantities, one or more conditional equations are available in addition to the observation equations. When the observations are a combination of observation equations and conditions equation, the most probable values may be obtained by the following methods, which are normally the normal equation, second one the method of differences, and third one the method of correlates. So let's see it. So if we talk about the normal equation, by avoiding the conditions equation and forming the normal equation of unknowns, it is done. Next is the method of differences. So direct methods of forming the normal equations for the observed quantities is suitable for simple cases. If the normal equations involve large numbers, it becomes very laborious to solve the simultaneous equations. In such cases, it is advisable to solve normal equations by the method of differences. The method of differences, which involves the use of corrections, is employed so as to simplify the normal equations. The method is based on the principle that the most probable value of the unknown quantities are assumed and the required corrections obtained. The equations are therefore formed in terms of the correction to the angles, which makes it easier to solve the equation. And lastly, the method of correlates. So the method of correlates is also called the method of condition equation or the method of Lagrange multiplier. So correlates or correlatives are the unknown multipliers, or say independent constant, used for finding the most probable values of unknown parameters. These are derived from the principle of least squares and conditional equations. Number of correlates required is equal to the number of conditions. The direct method of normal equations was used for simple cases, while the method of differences was used for reducing the arithmetic work. The condition equation was used to eliminate one of the unknown, thus giving one more observation equation. When the number of conditions equation is more, the method of normal equation becomes laborious. In that case, the method of correlates may be used. However, in the method of correlates, the equation of conditions improved by the theory of least square is used in addition to all the other available condition equation. So all the condition equations are collected in one place. This method is very advantageous as computations are reduced to a large extent. So here are some important questions which can be asked in your examination. So be sure you remember each and every theory. So here I end my session. Thank you all of you.